Hi everyone. Thank you for coming to another NL seminar at ISI. Today we have Shivanshu Gupta from University of California, Irvine, who is a PhD candidate advised by Samir Singh. He's been a research fellow at LinkedIn and Microsoft Research India. He's completed his bachelor's and master's in computer science at IIT Delhi. His primary research interests are systematic generalization, in-context learning, and multi-step reasoning capabilities of large language models. So without further ado, let's welcome Shivanshu.
Okay, so I'll be talking about a couple of works on in-context example selection, specifically how do you select examples that are actually informative and help the language model answer a given test input. So before we begin, let's look at like a bit of a recap of the NLP field. Originally, the traditional approach used to be to fine-tune a model on a labeled task data, where you would take instances to gradient updates, and then once you're done training, you would pass a new test input and use the model on that. But more recently, like with the emergence of larger language models, they demonstrated an ability to solve new instances, just given a new task instances, just given a prompt comprising a task description and a few examples. For instance, like they could translate English to French, given examples like sea otter is route to the mare and so on, and then just a test input, and more likely than not, they will give you the correct translation. And then it was also noticed that these models, this is from the GPT-3 paper, it was noticed that the models improve in performance as you give it more and more in-context examples. So in the x-axis, you have the number of examples. The models also, as they get bigger and bigger, they get better at using those in-context examples. So much so that more recently, in-context learning has become the de facto approach to leveraging large language models, which is good because these models are so big that it's like almost intractable or impossible to train, and often they're even hidden behind APIs. You cannot even train them. Another benefit of in-context learning is that it's been shown that it gets better generalization, for instance, compositional generalization and other OOD generalization. And because you're not training, there is no like forgetting, it retains all the parametric knowledge in the model. However, there is a really important problem in here, which is that the language models are really, really sensitive to what examples you put in the prompt, and even the order of those examples, so much so that it can range from like state-of-the-art to random performance. So in this work, and in this talk, I'll be talking about the problem setup will be that we are given a test input and a pool of say n instances, and we want to select a few, say k equal to 10 or 8 examples to put in the prompt for that test input. And what you want is that these instances are very informative about how to solve that test input. Now, before we go into like how you could approach this problem, you might ask like, why do you even want to select? For one, there is like limited context lengths of these LLMs. You cannot put like infinitely many examples. But these days, we also have like really long context length LLMs. And even then, you would want to select a few for computational efficiency, and also because LLMs are known not to use their entire context equally. So possession, ordering, everything matters. So now existing approaches include, so the standard approach of like, often people just use random example selection. But if they do something better, they often just use some off-the-shelf retriever like BM25 or cosine similarity using a general purpose encoder like BERT. And then like take the test input, all the candidate examples, score them using these metrics, and then take the top K and use them as the examples. This is obviously suboptimal because these are general purpose off-the-shelf retrievers. They are not specifically trained or like suited for in-context example retrieval. So the challenge is that like you could try to train a model for retrieval of such examples, but the challenge is you do not have a goal retrieval. You do not know what is a good example for a given test input. So recent approaches have tried to like circumvent this issue by some sort of training. to train a retriever for in-context example selection. These include task-specific training. They train on the particular task using which eliminates the training-free nature of in-context learning. They also often use feedback from an inference language model, the downstream very large language model. So the retriever usually is a small base size, a BERT base size model, while the inference language model could be anything from GPT-3 to Neo 2.7 billion. But because they use feedback, they can be costly, the training itself, and also limits generalization to a different language model. So if they train with Neo, they will not be able to generalize to a much, much larger model. So any questions about the setup? Otherwise, I'll start talking about the first approach. Right. So the intuition in our work in general has been that in-context examples should be selected together as a set, such that they demonstrate all the salient aspects of the test input. Now, here, by salient aspects, I mean task-specific facets or features like reasoning patterns, rules, or similar properties of a task instance that is necessary, task input that is necessary to solve them. So looking at an example here, this is an example of a semantic parsing task. You are given an utterance like at a meeting with Jim and his manager for tomorrow, and you want to translate into a logical form, an ambiguous program construct that represents that input's meaning.
Sorry, I do have a question, Roger. Are you doing anything at all with regard to instructions in these experiments?
Instructions, no.
So are there any instructions?
In the second paper, I mean, there is an instruction like describing the task itself. So translate this to this, or translate this input to a logical form. And then there are examples. So the primary focus is on the examples.
Okay,
the instruction
does vary depending on the task.
Exactly. But it will be minimal. We want it not to affect the results so much. Yeah. Because in fact, like the very first, the GPT-3 paper plot I showed, there is like the instructions and the examples have complementary effect on the performance. They give like complementary information to the model. Okay, so we want to translate a natural language input into a formal program. For such a task and this given input, the abstract, the salient aspects might be the operations that need to be produced in the output form. So like at a meeting needs to be translated to create event. His manager has to be like find the manager Jim. For tomorrow, it starts at tomorrow, and so on. Now, the model has to be able to translate these. It needs to see examples of how, like these functions, these formalisms. And suppose we want to select two examples for this input from those over there. We would definitely not want to select the first one because it doesn't demonstrate any relevant salient information. But because it's none of those examples demonstrate all the salient aspects, it's also a compositional setting. So we want more than one examples to together demonstrate everything. And in turn, it also requires compositional generalization from the model to compose information from multiple examples. So if you were to use a standard ranking-based approach, the one that I described earlier about using a retriever, scoring each candidate, and then ranking and taking top K, it would select C2 and C4 because they are individually most relevant, most similar to the test input, but obviously fail to demonstrate how to find the manager. Instead, we suggest that we should be doing a set selection. So we want to select C2 and C3. Even though C3 by itself may not be very relevant, it has some information like next week, which is not very informative for the given test input, but its marginal relevance is much higher. So given C2, you want to select C3. So based on this intuition, the way to operationalize what required to first, we want a way to determine these salient aspects. Know that we're not given what a salient aspect is. This was just an example of a task in a test input, but for different tasks, the salient aspects might be completely different things, something very abstract even. And we want also to measure the coverage of these salient aspects, such that if we were given the 4 instances on the left, we would get the ranking on the right. And then second thing we need is a metric that does the same thing, but at set level. So you want to evaluate entire sets of demonstrations and not individually. So let's, and of course, the set metric should rank C2 and C3 higher than C2 and C4. Okay, any questions? Otherwise, I can go into the approach. Okay. So let's try some ideas for how we can get into this. Suppose we wanted to use unigrams to capture these salient aspects. At the top, we have the different unigrams in the test input, and on the right, we have all the candidates. And the numbers here indicate whether there is a unigram overlap. First thing to note is that like unigram is obviously like very, very sensitive to the surface form. It is not able to count for synonymy context. So appointment is not matched with meeting, and I guess boss is not matched with manager, and so on. So the score that you get out of it is not very reflective of the actual relevance, even though C2 and C4 have almost identical information in terms of like the logical form they'll produce. C4 is ranked much, much lower than C2. So as an aside, all n-gram-based metrics like PM25 I mentioned earlier, and any other DFIDF metric faces this limitation. So what we want is something that is first of all very like capable of taking into account these paraphrases. Should be, and if you do that, you would get a ranking which is much, or a scoring which is much more reflective. So if you match meeting and A with an, then you'll be able to get C4 up to 7, and then C3 will not be very far behind, but worse than C2 and C4 because it shows some additional information that is not relevant and pays to show some other. Okay, so now what is such a metric? The metric that we choose in this work is birth score. It was proposed originally as a language generation metric, or an evaluation metric for language generation tasks like summarization, translation, etc. The way it works is that suppose you want to check whether the candidate it is freezing today has the same information as reference, whether it is scored today. It will use encoder model, say like PERT, to get contextualized token embeddings of all the tokens in both the candidate and the reference, and then match them pairwise to produce a matrix of scores like this. Here, the reference is on the side and the candidate is at the bottom. And then if you take the row-wise maximas to get the scores on the right, those can be considered the coverage of the recall of each token in the test input, or in the reference in this case. We can use this for our setup of example selection by using the test input as the reference and all the candidate examples as the candidates. And then in a formula, this is what it will look like. It would be a summation over all the test input tokens of the maximum cosine similarity it receives with respect to all the candidate tokens. So the salient aspects are very useful for the salient aspects would be very effectively captured in these contextualized token embeddings. They would not be affected by all the things of surface form issues, and also long distance, like will be able to take into account all the context. And another thing, birth score, the original one is not just the metric I computed here was birth score recall. It's a recall of the tokens in the test input. Birth score also computes the precision by taking column-wise maximas, and then using those recall and precision computes the F1 score, which is the standard birth score. Because we only care about coverage, we hypothesize that birth score recall should be enough. I won't be showing those results, but we do actually find that birth score recall is as good or better than the full birth score, and birth score precision is worse. Okay, so this is a metric for evaluating individual instances for their how well they demonstrate the salient aspects of a test input.
And first score, as I recall, is for comparing sentences.
Yes.
What you have here is like a token-wise comparison.
Yeah, so BERT score internally does a token-wise similarity and then aggregates that into a sentence level thing.
So Z is allowed to match multiple times to multiple X's.
Exactly.
So you can have a really degenerate example where Z is something pretty, there's only one token that's pretty generic and it just matches with every word.
Right, but the cosine similarity will be pretty low in that case. So suppose there is like it is matching pretty low for most of these things. It has the token score for it as the candidate token is pretty low for all the reference tokens. Or all the reference tokens.
Yeah, in my experience, I found that BERT score sometimes is like really degenerate.
Yeah, I can imagine, but at least for the goal of example selection, it seems to work pretty well. So
Just wondering, is there any like a punishing factor or like a confluent sentences? Separate tokens, like if every token is like is generic enough, like it's going to have a
right. We didn't like I guess the instances we were working with, the tasks we were working with, some of them might have had instances which are not very like fluent as well. I'll show the tasks later. So in fact, there are some tasks which are generated it's a systematic, not by human written, but synthetically generated tasks. Those data sets, so those are expected to be not very fluent, and yet the model works. The method works well. What is going on with this?
Disconnecting.
Now it's there we go. Okay, any other questions?
This is a real example that you showed here between the weather is cold today and it is freezing today.
So this is an example from the BERT score paper.
Okay.
This is not an example of example selection in correct example selection. This is So in our case, that the candidates and the reference will be a test input. The candidate will be in a candidate example and reference will be a test input. This is just for demonstration of BERT score. Okay, so we have a method to evaluate individual instances. How do we do it for entire sets of instances? So first thing to note, the metric I described earlier is a sum of some metric for individual tokens of the test input. And metrics like BSR, the BERT score recall that I just described, TF-IDF, PM25, cosine similarity, they can all be written as such a sum of a coverage of individual salient aspects, where the definition of salient aspects differs for the different metrics. For BERT score recall, those were the tokens, the unigrams, and their contextualized token embeddings. For BM25 and TF-IDF, they will be the terms you are using in your it could be unigrams or higher level n-grams and so on. So they can all be written in this form, where you have a summation over some aspect, something in the test input, and then a coverage score for that aspect. Any such measure, any such coverage measure we show in the paper can be very naturally extended to the set level metric, where instead of giving the metric a single test input, a single candidate example, you give it a set of candidate examples, and then just stick in a max in here. That's all we do. The idea is that then you are matching that candidate example, the salient aspect, and trying to find the maximum coverage it can get across all the candidates you have. If you were to do the same thing for BERT score, you would get set BERT score recall. You have a max over here. So what you're doing is, for each test input token, you're finding the most similar candidate token across all the candidate examples. If you do that, you get the ranking you want. C2 and C3 will rank higher than C2 and C4. I don't know how clear it is from the back, but I'll show it in action. So this is a simple extension, very naive extension, but the best part is this extension is submodular for any coverage measure. anything you start from here. If it is of this form, this will be submodular. This is good because a naive way to optimize a subset metric would be to do a combinatorial search, try every combination of, say, k examples, and then compute this metric and see which one is the best. If you have a submodular measure, you can do it greedily. So you select one, then select the second, which maximizes that, then select the third, and so on. And let's see it in action. So
it's interesting that like the form of set coverage is conjugate to the particular form of Bert score recall. What I mean is it's max over a thing. Right. The way you define it, it kind of like implies that the inner metric need not be conjugate. That's C of SZ.
Yeah, it could be any
max.
It just has to be positive valued. Small c always has to be positive valued, and if that is the case, then you can make a submodular version.
So it's just a coincidence.
I mean, so I just did the proof on this thing, assuming an arbitrary c, and it just works. I don't know about the conjugacy and if that.
I'm just thinking about like in the particular case of ZPSR, right? Like you could just redefine Z to be like all of the tokens in all of the sentences, right?
Right.
And that would work. And I mean, it's not generalizable.
Yeah.
In this case.
Yeah. There is also the issue of like you cannot just drop the notion of the sentences because the greedy selection will be one by one on the sentences. So at any point,
no, I'm saying, okay, sorry. If you, I guess if you redefine the sentences to just be like the string of all sentences put together, of all Z sentences put together.
Right. So you will get a score for all the candidates together, but that doesn't give you a method to find the optimal subset of those.
Oh, right, because you have to choose the elements in Z to return.
Right. So suppose you have 100 examples. And the capital Z could be any subset of 10 examples. You want to find the optimal subset of
right, okay. Because set covers the score, but then you have to go from the score to the set.
Yeah, and that is where the greedy method comes in. Because you could do it combinatorial search, but that's going to be exponentially bad. So you want something that can be optimized efficiently. And to see it in action, we start with the same matrix we had earlier of a nice metric that takes into account paraphrasing, which gave C2 as the highest score, C2 the highest score. And so let's call it a pseudo set VSR because actual set VSR would not give like 0 or 1, will have more softer scores. But if we start with that, in the first iteration, we'll pick C1 because it has the highest score, set score.
C2.
Yeah, you're right. C2, that's a typo. And then if we were to select an independent ranking based approach, the second element that you would select would be C4. And then you would miss out on, again, the find manager thing that as I mentioned earlier. The greedy algorithm, on the other hand, would try all the other instances like C1, C3, C4 along with C2, and then compute a set score on each of the tokens. So this is each input tokens maximum coverage it can get out of the set instance, the set tokens. So for instance, C2 and C1 and is only appearing in C2 and not in C1, but the number here is 1 and so on. So if you do the set score, then the highest aggregate you're getting is from C2 and C3. And so the greedy algorithm will select C3 next because C3 is the only one demonstrating find manager, and we're good. Okay, so any questions about the approach, or I can now go into the results?
Wait, hold on a second. So the actual algorithm in practice, right? We're gonna the top level thing is to go over the words, the yellow words, right? So first we're gonna look at at, and then we're gonna find the argmax of the argmax in Z for score. So you get in fact you actually have to arbitrarily break a tie between C2, C3, and C4, right? Because they each have a 1 there for add.
Right. So what I actually do is you for the first step, it's basically just birth score. You compute the birth score of the input with C1. Birth score would be the score over here. There is no tie breaking needed for that. So you just compute the word score for like this.
The sentence level word score.
Yeah. So you get a score over here.
Yeah.
And the time might happen that two different sentences have the same score, but not in the token level.
Okay. What's your round two? The round when you select C2.
Right.
And then
Round two is selecting something other than C2.
And you say like C2 and something else. Okay.
Yeah. And then that is the bag of like sentences. So then you would be
so you're actually iterating over your sentence selection.
Right.
Well, I get. Oh, but you're stopping once you get the number of sentences.
Exactly. We want 10 sentences. I guess I should have mentioned that. So we will keep doing this till we want to get the requisite number of sentences.
Okay. But the greedy algorithm is not the same. Is not shaped the same way as the actual like set PSR, right?
Set PSR is actually optimizing set PSR or any set the set extension of the R. Good, nice.
Can you go backward?
So
PSR is sum over all S in X subtest max Z. So the top level part of the algorithmic part is for each word in X subtest, but you just said it's not that what you do. Right. The outer summation is over the words in the test set.
Right.
Not the Z in big Z.
Right. So let's go back to the second iteration. In the second iteration, I'll be summing over the maxes. These are the maxes of the coverages the token add will receive from C2 and C1. These are the maxes.
So your capital Z's keep on
changing.
You're changing. You start off with just like a single element in each C, capital Z. Okay.
Right. At the very first step, you have empty set, and you're trying to extend that into one, and then you have a one set, and then you're extending that to a two-size set. Right. So so there are some other technicalities. What happens if you run out of instances to add and you want to select more? No, the more interesting one is there is no sentence that would increase the set score any further. In which case I just reset. So we have selected say 5 sentences. Now we're gonna start selecting a new set of new covering set because there's nothing that extends to six element set that further increases the.
But you have to eliminate the 5.
No, you don't eliminate. You keep them,
right?
And then you start independently.
I mean, isn't the implication that it would be redundant?
But yeah, exactly. It's a redundant information.
So
but we want to select 10 instances, so that's the reason why the model is getting more of that same information.
So you keep that 5 and you choose another 5.
Yes, you restart.
Like if, for example, your pool was the identical set of sentences twice, then you would pick the first 5, and then you would pick their copies, which would that would be the optimal thing to do.
Yeah.
And so those 5 good sentences, the same 5 sentences cloned, and then 100 sentences that are totally garbage, right? Like you want to
based on this score.
Correct.
Okay, so because we are already at half an hour mark, I will speed up a bit. Right, so the very first results are with semantic parsing data sets, a bunch of them, SM Calflow, GeoQuery, Overnight, and Top Break. I can tell more about the specifics of these data sets, but the high level is that in the different columns, we have language models of different sizes, strengths, different types even. Starcode is a code pre-trained language model. Some of them are not, some more general language models. And then in the rows, we have different selection methods. This is still in, okay. And this is 8 short in context learning performance. So we are selecting 8 examples and then doing in context learning with the given inference line. So one thing to note, BERT score recall outperforms all the training free selection, like random selection or off the shelf KNN cosine selection, BM25. Doing set selection on top of that. So instead of just selecting individually and taking top K, you do an entire set selection together, gets much more performance. And then it even beats trained methods. So even though this is just an off-the-shelf general purpose encoder we are using with BERT score, EPR and CEAL are 2 prior methods that train with GPT Neo as the has an inference language model to give some signal of what is a good example, and then use that to train a retriever. It is even able to outperform that. What's even more interesting is that its improvement itself improves as you go to a larger, more powerful language model. So these are organized in ascending order of like strength and size. And then like up to codex, it starts getting 17% on average improvement over cosine similarity. So we analyze this, improve this increase in across language models a bit more. So here we have two different types of splits for semantic parsing data sets. One is the standard IID split where you just do the in-distribution evaluation. There are some training questions and some test questions. There is what is called a compositional split where there is a compositional generalization required. So if the training time you're given instances like step files and jump, and then the model needs to combine information like in the test time. So it needs to understand what is to jump was. First thing to note, EPR and SEAL, because they are trained with NEO, their performance improvements goes down as you go to a more stronger language model. So NEO versus Cortex. And what's more, set BSR, the gains, as I showed earlier, improve when you go from NEO to Cortex. So essentially what is happening is that the larger language models are better at compositional generalization. They are better at composing information from different examples. And set BSR is able to take advantage, leverage that.
Did you try doing any of the GPT 3.5 tuning?
This was not at that available at that. This is last year, Feb. Are you saying GPT 3.5 fine tuning?
Yeah.
Yeah. You can find some GPT 3.5.
It's can cost a little money, but you don't.
Yeah. So I guess money
you don't
was
need a lot of examples.
It's really easy. Yeah.
But this is about in-context learning, so I don't know where.
Well, because you're comparing to the EPR and the
Oh, those are methods that train retriever. The language model at the bottom is not trained at all.
I guess I'm thinking back to your previous slide where you have the trained. Aren't those intermediate results trained fine-tuned results?
Yeah, so those are they train a retriever like say BERT to select the examples, and then they give the examples to any.
Okay. So you're not directly comparing fine-tuned.
Yeah.
Work.
No. Yes. Yeah. We're not comparing to fine-tuning. This is all in context learning.
Got it.
Yeah. Yeah. So these are all like different approaches to select examples using some retriever, then give it to some language model. One of these. Right. What's more, this set extension also, like I mentioned earlier, can be applied to other things. So if you apply to cosine, BM25 with different types of terms, like the terms, 4 grams or something else, or bird score, it improves performance in compositional settings as expected. We also evaluated on a few non-semantic parsing data sets like mathematical problems, question answering, NLI, firefighters detection, segment analysis. And we found that bird score recall improves performance even beyond semantic parsing, even though like all it's doing is just matching tokens. It's able to improve, like completely outperform all the other training free methods. Set BSR does not work because it's meant for improving compositional generalization, like it's meant for setting where no single instance might show everything.
It does work in a vanilla. I just highlighted the wrong thing.
Yeah. Oh yeah. Yeah. Okay. Fine. But yeah, so not so well because like many of these instances might have a very similar instance in the training, the selection examples. Okay. So in summary, set BSR and BSR are both very easy to use, training free, use something off the shelf, and they can potentially outperform state-of-the-art training methods, for example, selection. BSR is generally effective, set BSR improves performance and compositional settings. But there are two major limitations of these methods. One, the selection speed. So they require matching, like if you were to do cosine similarity-based selection retrieval, you would just compute a single embedding and do cosine similarity of that. While here we are computing token embeddings and then doing pairwise similarity and then doing maps or whatever, which makes it quadratic compared to in the length of number of tokens compared to cosine. The other issue is that these are still general purpose encoders and not everything will be expressed in text and can be matched. So, excuse me. So in the next work, we begin from scratch. We think about what we want. We want a task-informed relevance metric that captures the task-specific salient aspects, such that these test input, given the test input and these candidates, we get this ranking. Now, obviously, preferably one that's fast and training-free. You could train an encoder, like I mentioned earlier, one that could map C2 close to the test input, C4 a bit further, C3 much more, and C1 just completely far away. But we do not have the gold annotations, so we cannot do that. The idea that we came up with was to train a model with some sort of a bottleneck between the inputs and the outputs. So the idea is that the bottleneck will need to encode all the salient, all the most important information in the inputs that's necessary to produce the correct output, to correctly solve that input. And if you are able to extract that information in some way from that bottleneck, it might be useful to also identify the good examples, the good in-context examples.
So what are the inputs and outputs here? So inputs are all the samples that you have?
No, sorry. So this is just any task. Suppose you're doing sentiment classification, then the input would be, say, a review, and the output would be the class, the positive or negative.
Sorry, this was a question that was asked earlier, but I only saw it just now.
Yeah.
But I think it's still relevant. Yubo asked, can you explain the difference between informative and relevant? Relevant or similar? Like, so is the existing retriever, is it trying to select more relevant instead of more informative?
Yeah, that's a good question. So it's not a very clear thing. Relevant is a more general term. What is more relevant to the given input? And I guess you could say that the standard retrievers are finding the most similar thing and hoping that becomes more relevant. While we say that what we want is something that is very informative to the test input, to how to solve that test input. And that informativeness is what is relevance for us. So relevance is what we want, but we characterize it as informativeness compared to similarity for the previous work. Right? Or the standard. I mean, the ones that train also get a more informative relevance, but ours is even better than that.
Gotcha. Okay,
so to operationalize this, the way we do it is that we do this sort of we train a encoder decoder model where there's an attention masking bottleneck between the decoder and the encoder. So the encoder gets as input the task input, a review in case of sentiment classification, and a few tokens, some tokens called gist tokens that don't have any meaning. We just add them to the vocabulary. There is usual self-attention in the encoder, but the decoder can only attend to the gist tokens. So any information about the input has to pass through and has to be encoded into the gist tokens for the decoder to be able to produce the correct answer. So if you do fine-tuning based on this, the model will be trained, the encoder will be trained to encode, given any input, the information in the gist tokens activation. After training, obviously, the decoder doesn't matter. We can just drop it. And to just a new input, you just pass the same sequence, X followed by a few tokens, say L tokens, and catch the activations above those tokens. One thing to note, these can be one or like any number of tokens. So to use this for example selection, we compute the gist embeddings for all the candidates and the test input. The gist embedding in this case would be just the final layer activations of the activations that we cache for each input. And then we compute a score that we call gist score, which is very similar to the BERT score I showed earlier. Given input and a candidate example, it computes a sum over the input gist tokens. Suppose there are L of them, sum over them, and sum of the maximum cosine similarity each input gist token can get with the candidate gist tokens.
Sorry. You're training the gist tokens, you're training the gist representation,
right.
And there's a bottleneck of
attention.
But when you're training, you are back propagating from the gist tokens to the encoder, right?
Right.
So how's this different from a CLS token?
How is different?
From like a CLS token.
CLS token is very similar, except it's just one, and it's an encoder model. While we haven't, so CLS token cannot be used for like the generation task. So if you have,
but you're using the gist tokens as attached to the encoder, which is essentially the
exactly.
CLS token.
So yeah, and then there's attention masking, preventing. So it is similar, but it's a distinctly different approach where we are using an encoder decoder model with attention masking to ensure just tokens are what the decoder attends to.
Okay.
CLS is,
think about like instead. Okay, so you're putting a decoder on instead of a classifier,
right?
But the encoder structure is identical to BERT.
Right.
It's attention mask.
Not the encoder.
No.
The encoder to decoder. So the CLS token is
right. That's full attention and a CLS token or tokens.
Right.
Then those CLS tokens are the only thing that's connected to the decoder, which is not a classifier.
Yeah. So if you think of it like that, it's a small jump.
Yeah.
But the CLS tokens have only been like trained one for some proxy task for language modeling that helps in getting good language modeling, and then has been used for encoders. Yeah. So I mean, you can use such an approach for classification using the CLS tokens to then put a classifier on top of it. But it takes much more than that. Like you have to have a decoder or something like that to do it for other tasks.
Yeah. Okay.
So that's the contribution.
Okay. No, that's fine. It's fine.
Right. Okay. And so even till now, what we have is I forgot to mention. So this gist score, it's also a coverage measure. It's also a sum over inputs, gist tokens, and so can be extended to a set metric. The thing I described earlier requires training for each and individual task, which is not very ideal. So we also explored a multitask pre-training, where we train the model with the encoder receiving the instruction as well as the example input, and then the same gist tokens, the decoder can only attend to the gist tokens. The instructions allow the model, the encoder, to infer the task specific information into the gist tokens, so that like for any new task and any new input, you pass the model T, X, and G, and then cache the activations above G, T, and X. And you can use them for gist code like I showed earlier.
So the practical benefit of this approach is that you can do this encoder decoder training with a smaller model, and then that way select examples to use for a larger model.
Exactly. Right.
Because otherwise, if you have the large model and let's say theoretically you can train it, then it might be just better to train that model.
Exactly. Right. Yeah. So the whole point is that, I mean, even when you're training a retriever, you're only training a smaller model to select examples for a much larger model. But even that training step is non-ideal. Like that creates a hurdle before you can get example selection going. So this completely removes that as well. Like this brings it down to the level of using an off-the-shelf encoder. You can just use our multitask pre-trained model for any task you want.
But you still need to do training at least.
No, there is no more training. So
you have to train this.
We have training. Yeah.
You've done it for everybody else.
Yes, exactly. Okay, so results next. We evaluate this on a whole bunch of data sets. In particular, we included some composition generalization evaluation, some non-English evaluation. And because we have a multitask model, we also evaluated on held out setups, like held out domains. Treat eval is a treat data set, while med-NLI is a medical data set. And also semantic parsing is held out corpus, held out task for the multitask corpus we use. I don't think I will, or I will describe it. Okay. So I will be referring to the fine-tuned model as GSF. L will be the number of tokens. Unless specified, it will be just one token. And the multitask model will be GSM. For them, we use plant 5 and plant base and large respectively, because it's a multitask training. We needed to do a large model. The collection we use is a subset of the plant 2022 multitask collection, which does not contain semantic parsing, and hence why semantic parsing is a held out task and a very hard evaluation. On training free compared to training free baselines, in the rows we have the different selectors like random, PM25, sentence bird, PSR, all training free, and different language models in the columns, again arranged in an increasing order of some increasing order of hardness. Neo, Llama 7 billion, Llama 13 billion, Mistral, Zephyr, Babbage, and Da Vinci. The multitask model consistently outperforms all the training-free methods. These are averages across all the 21 datasets and splits. And then the fine-tuning obviously further improves performance and creates like a much higher gap between the standard approaches. We also compare with trained baselines. So at the top, we have comparison with the EPR and SEAL methods I showed earlier on a few specific datasets. And at the bottom, another trained method. Again, it trains with feedback from a large language model, Llama in this case. And so GScore, the fine-tuned one, consistently outperforms. The purple bar consistently outperforms all the prior, both of them, all three of them. And then GSM, the red one, is also pretty competitive. It's a bit less than the fine-tuned one, but more than all the training-free baselines, even though it does not require, it's just used out of the box for all the data sets.
There's a couple of cases where it is much worse.
Exactly. So so those are the semantic parsing data sets. And this is one token. So I'll come to semantic parsing data, but they tend to require more than one tokens. So just an aside, number of examples, even if you vary it, you get consistent improvements compared to the baselines. Okay, and like with just 2 examples over here, GScore is able to outperform the standard methods with 8 examples. So that's like very efficient as well. You don't need to give it all the examples to the language model. And okay, so these are some held out results specifically for the multitask model GSM. We have some NLI data sets, some paraphrase detection, some sentiment classification. And then we have the medical and the tweet on this side, some non-English data sets. GSM again beats all the training-free baselines except I guess med-NLI, birds per recall a little bit higher, and then the NLI ones a bit higher. But it's pretty competitive with all the training-free baselines or better. And then, okay, so this is results for semantic parsing. We found that unlike most other data sets, just one GIS token was enough. They didn't require more than one. Like it was enough to encode the right information. But for semantic parsing, because there is information like different phrases that map to different functions, we found that we needed more than one tokens and also set selection. So that is what this plot shows. On the x-axis, you have the number of GIS tokens. And on the y-axis, you have the average semantic parsing performance. The solid lines are with set selection, and the dashed ones are without set selection. We also have birds per recall, which obviously is a straight line because it doesn't like vary with just tokens. The multitask model is able to like match the set PSR, even though it was never trained for semantic parsing. And then the fine-tuned model like completely outperforms set PSR. I wouldn't be showing it, but it also outperforms the trained methods. And I also didn't mention EPR and SEAL. EPR selects individually, like independent ranking, while SEAL is also another set selection method. So set GSF outperforming that is like our set selection method outperforms that. And although PSR was better than the multitask model, at some points it's much, much, much slower. So because it's matching each and every token, while we have to match only like a few tokens. Here we have speed ups with the multitask model versus different selection methods on many different data sets. PSR is like tens of thousands of times slower in some cases. Surprisingly, we even found it to be faster than BM25 because like for just score, we can do it all in our GPU. Like the entire scoring with respect to all the candidates can be done in a single GPU call, like because of matrix tensor algebra, while BM25 needs to do for loops and stuff like that. Right. Okay, so some good things, but we also identified something really interesting while analyzing the performance of these models. So I'm going to be plotting the classification accuracy versus the precision of the different selection methods for classification methods. So precision being if the model selected 8 examples for some test inputs which had positive label, how many of those 8 had the same label as the test input? What fraction? Is the retriever just selecting the label that the model has to predict for the test input? So that's the point you'll be seeing. The points are for a data set and a selection method combination. One thing, the selection accuracy, the selection precision and the ICL accuracy are both higher for just score methods compared to the baselines. But the most important thing is that it's very highly correlated. So it seems as though the retrievers are basically taking care of some of the classification itself. Like they are surfacing the right, like the examples with the correct label that the model then predicts, and might be the primary driver for improvement in classification performance.
You're looking at as if the answers to the things that you selected were the classification labels themselves.
Exactly.
How does that work for the complex classification tests?
We cannot. So this is a finding just for classification.
Oh, so like semantic parsing is not.
Yeah. Okay. So this is basically a commentary on the state of example selection approaches that we just found that not just ours, but all prior, the ones that we looked at, are just like for classification methods, you're just surfacing the test input, the examples with the same label as the test input. So
it's not just correlated, they're also often the same number.
Yeah, it's really, really close.
Well, that implies that much faster algorithms are doing classification.
Yeah, majority vote.
What retrieval?
Retrieve, then majority vote.
Yeah, I guess so. But like you don't have to use your decoder at all. Right?
No, so in this case, it's a downstream language model being used to solve the task. A retriever is retrieving examples, giving it to the language model, say GPT.
Yeah.
In this case, what this is saying is that you can just use the retrieved examples to majority vote accuracy. You don't even need to use the GPT.
That's what I'm saying. So,
yeah. And I mean, it might work for, so first thing, there are a few caveats. Larger language models, the inference language models, are less sensitive to the strength of the retriever. It's not very clear. All the takeaway is just that, where is the cursor? So Zephyr is the highest. Like the bars themselves, the relations are going higher. So given the same selection precision, a stronger language model will get higher performance, basically suggesting it's less reliant on the retrieval performance. And yeah, exactly. So for other tasks, we look at the performance of the chess model itself. So we were wondering how like we trained a model, an encoder-decoder architecture, and then we dropped the decoder. But the encoder-decoder was trained to do a task. So you can compare the performance, like look at how it affects the downstream ICL performance. And that's the GMF baseline. So just use the encoder-decoder with the bottleneck on the task test inputs, test data set. And then there are ICL baselines where you either random or sentence per selection, or the just model used to select examples and solve with Zephyr. The key findings are that, so this is what I just described. the key finding is that ICL can often outperform the underlying fine-tuned model. So although in classification we found there is a really high correlation, for more complex tasks or like tasks, even classification, which are much harder, the language model can extract more juice out of those examples. And more importantly, there are some tasks that are just impossible or like really hard for a fine-tuned model, like compositional generalization, which has been very well studied to be something really hard for fine-tuned models, or even GSM-8K, like chain of thought reasoning, which is an emergent capability. A small language model may not be able to do it. And completely fails zero accuracy, but still able to improve the performance of ICL. So 39 is more than standard encoders, 16 with 13. Yeah, so in some way, it's combining the strengths of fine-tuning and ICL. Of course, the question is then how is, like, if the model completely failed on SM-CalFlow and GSM-8K, how was it even able to like select the right examples? So, and on the other side, like we decided to look at the information encoded in the chess tokens to see what sort of information they're encoding. So for GSM-8K, we found that even though model completely fails on it, it's able to encode information like whether the question requires multiplication, division, and so on. For SM-CalFlow, things like whether it requires some temporal reasoning or organizational reasoning. And that's how it's able to surface the correct examples, even if it's not able to solve those examples. And for other data sets, like for MNLI, as expected, it's able to encode the class labels themselves, which in turn results in like very high selection precision. For CMSQA, it's able to encode relevant concepts in the question, like whether it's relating to animals or some social things, so on. So in conclusion, our example gisting models can extract task-specific salient information that is useful for selecting in-context examples. And then fine-tuning these models gets state-of-the-art ICL performance, while even the multitask pre-trained model, the GIST core is able to generalize to new tasks and outperforms prior training-free methods. And because if it's like much better trade-off of performance, ease of use, it's like a good candidate to be used as a next standard approach. Yeah, so thanks my collaborators and thank you everyone. Samir, Matt, Ethan, and Clemens. Yeah, that's all. Take any more questions.
Awesome. I think we asked a bunch of questions throughout the talk. And since we're at time, I think we can call it an end here. So let's just thank Shivanshu once again for his. We go. I have a very quick announcement to make. So next week we have Kevin Knight giving us an in-person only talk at ISI. His talk will be on 30 years of perplexity, where he discusses how the task of predicting the next word has led to many NLP revolutions and enhancements, and how he thinks it's connected to AGI capabilities. So I think that would be very interesting. So stay tuned for that. Thank you.
Thank you.